The next speaker in this poster session is Gabriele Dragotto from Polytechnique Montreal, and is going to talk about when Nash meets Stackelberg.
Thanks, Carla. So I'm gonna quickly present you a series of works that we've been doing in Montreal with Margarita and Shriram that are in the audience right now. So we have a pretty good plenary on Stackelberg games, and we're gonna talk again about Stackelberg games, but here we don't have nodes and vertices, but we have bagels. So imagine we have a series of bagel shops. For instance, in Montreal, we have this very good bagel shop. It's called Saint Viateur. And of course, it's trying to sell bagels in a market in order to profit. But at the same time, we have another bagel shop, which is Fairmount. And so we have a kind of a competition in the market for the sales of bagels. And well, at the same time, we have a kind of a higher level interaction in the form of leader-followers interaction played by for instance, Montreal city governments that is kind of taxing the bagel shop, for instance, because their ovens polluting. So this is kind of a Stackelberg game with perfect information as the one that Ivana was talking about. So now let's imagine that we have a series of Stackelberg games, and all the leaders of these games are actually playing a Nash game between themselves. So we have, for instance, New York doing the same for bagels. Well, we call these kind of games Nash games among the Stackelberg leaders. And well, if you don't like bagels, you can replace bagels with energy producers, and you have a kind of a international energy trade scenario that arises. So I'm gonna just quickly mention again some characteristic of Stackelberg game. Well, generally, most of cases are NP hard. The feasible region for the leader, as mentioned, sometimes is non-convex, not even connected. But under certain assumption, Shriram and Amitabh have basically proven that the feasible region looks like a unit of finitely many polyhedra. And I'm gonna also mention another important concept that is one of Nash equilibrium. So imagine we have some players, and each player is solving kind of a optimization problem, a MIP. We have an equilibrium whenever basically we fix all the other player decision and we solve the optimization problem of the player I, and we do this for all the players, and we get kind of agreeing a mutually optimal strategy. So we kind of have a situation in which the answer doesn't change. And well, then theoretically, you know, we distinguish between mixed or pure Nash equilibrium based on the support size of such structures. So I'm going to present you 3 results about this NASP games. The first one is about complexity. So we have proven that also under very, very restrictive assumptions, so very simple NASPs when we have just 2 leaders, so 2 cities, and just 1 bagel shop for each city. Well, deciding whether this game has a mixed Nash equilibrium or not, usually it's sigma to p hard. Well, there are some cases in which we can say there exist, but still the result is surprising in the sense that it's not PLS complete as many equilibrium problems in game theoretical literature. So how do we tackle these games in terms of MIPS? So we kind of consider the feasible region of each leader, which are finite union of polyhedra, for instance, 4 polyhedra. What we would do in MIP is, well, we use some kind of convexification, for instance, the Balázs closure of the convexel. Then we compute a solution for this game over the hull. And well, if it is a MIP, what we do is we kind of find some disjunctive arguments if the solution lays in the hull but not in the feasible region, and then we cut it off. But since it's a game theoretical actually application, we can interpret this point laying in the hull as a convex combination of feasible points, and in a sense, as a mixed strategy Nash equilibrium. So in a sense, we're not throwing away any feasible solution. So I'm gonna present you 4 algorithms that we have developed. They're valid for NASP, but they're also valid for generic Stackelberg games. So we are not restricted. So the first one is a field enumeration. as I told you, each leader of this game has a finite union of polyhedra. So what we do, we enumerate all these polyhedra, we convexify the feasible region, and then we solve this kind of bigger game. And whenever we get a point also in the hull, we are guaranteed that this point is a mixed Nash equilibrium. And of course, this algorithm is complete and exact. So in a sense, either we get an equilibrium or a certificate of non-existence. The second algorithm, it's kind of the idea is very simple. So you don't consider all the polyhedra, but you start, for instance, with one polyhedron for each player. And then you solve kind of a game with this restricted feasible region. And well, if you get an equilibrium, for instance, you can check whether this is an equilibrium for the original problem by solving a MIP, where you basically parameterize all the other player decision, and you check that the response for player I coincides with the equilibrium. Otherwise, well, for definition, you have a deviation. So there's a player that is better off. And at this point, what we do is we identify the polyhedron that contains the deviation, and we add it to the inner approximation. We take the hull and we iterate. Worst case, well, we hit the field enumeration. In practice, this, well, I would say never happens, and we're better off. Third algorithm, it's actually a heuristical algorithm. So say you're interested in having pure Nash equilibria. Well, if you have a pure Nash equilibria, basically you cannot lay inside the interior of the convex hull, but you have to be strictly in one of the original polyhedron. So what we do is, well, we take one polyhedron for each player, and we compute basically an equilibrium over this restricted game. If we get an equilibrium, we are basically sure that this is a pure Nash equilibrium for the original game. If not, we test another combination of polyhedra. There is a little technicality. This algorithm might never terminate. This is why we call it heuristic and not like fully complete algorithm. The fourth one is an outer approximation. So we go the other way around compared to the inner one. So again, we have this feasible region made of union of polyhedra, in which we have some common constraints and some complementarity equation in the form you see in the third line of the set. So this perpendicular sign means basically x times z equals 0. So basically what we do is we start by just taking the relaxation of this region for each leader. So we take just the common constraints and the non-negativity one. And then one at a time, we add the complementarity equation. We select a complementarity equation, we add it, we compute the closure of the convex hull, and we iterate. We have a similar way of checking whether the equilibrium that we get is also an equilibrium for the original game, but well, it's still work in progress, and plus it's out of the scope probably of this posture. In terms of computational results, well, for generally mixed Nash equilibrium, the inner approximation performs better, of course, to the field enumeration. We test usually our problems with instances where we have 3 to 7 leaders with respectively 1 to 5 followers each. And for what concerns only pure Nash equilibrium, so when we specifically seek for pure strategies, well, of course, the combinatorial heuristic, it's almost 7 times faster than a field enumerative approach. So last but not least, actually, we are building an open source solver that handles all these kind of problems, Stackelberg games, Nash games, NASP, and some classes of LCP. And it has some APIs for energy trade markets. Actually, it works with Gurobi, but we're planning on integrating it with other solvers. So in a sense, what we're doing here, it's in the intersection between MIP, because we're exploiting the algorithmic arsenal and the well and very good polyhedron and theoretical understanding from MIP, And we are intersecting it with basically algorithmic game theory that is allowing us to model this complex interaction between agents. And we're kind of giving a new interpretation of a convexification approach for games. And well, last but not least, there are some nice applications, especially in energy markets, when you want to kind of model environmentally efficient markets. Well, NASPs are very actually powerful tool to do so. So we laying kind of in the intersection between these three different areas. Thanks for your time.